Okay. Good afternoon, ladies and gentlemen. It's my great pleasure to to give a talk here. First of all, I would like to thank the conference organizers. Today, my talk is about the interference effect in E2E electron momentum spectroscopy of molecules. Here is the outline my talk. Firstly, I would introduce about the background and our motivation. Secondly, I would talk about vibrational resolved EMS of H2 for looking young-type interference. Then I would turn to the EMS experiment on polyatomic molecules for looking multi-center interference. As well as we all know, particle wave duality of matter particles play important roles in quantum mechanics. This revolutionary conception is demonstrated by electron young-type double-slit experiment. Since then, such young-type double-slit experiments shows the wave character of large particles, including the fluorines and the huge organic molecules. Another way to realize the double-slit experiment is proposed by Cohen and Funnell in the photoionization of diatomic molecules, in which coherence spreads of electrons emitted from the two atoms in diatomic molecules is often regarded as molecular double-slit interference. Such interference effects can lead to the oscillation in energy or angular dependent cross-section. Until 2001, 35 years later, this prediction is proved by the ionization experiment by ion exclusion. And another 4 years later, it was proved by photoionization of the diatomic molecules. For electron impact ionization experiment, it was proposed by Steers in the calculation, and then was proved by the experiment. This interference effect was revealed from the suppression or enhance of the binary peak or recoil peak in the cross-section as compared helium-free atoms at the same kinematics. Now the question is can we observe the young type of interference in binary E to E? What is binary E to E? For binary E to E, we have a high electron impact energy and large moment transfer to ejected electrons. This field is introduced the last speaker, Professor Takahashi. In this method, near the base region, the incident electron transfer all the lost momentum to the target electron. In this analysis process, the residue ions act as spectators. Through detect two electrons in consonance, we can obtain the binding energy and distribution of electrons. And the measured E to E cross section is related to the wave function of the target. So for binary E to E, it's also called electron moment spectrometer, also EMS. For H2 molecular, we can use the LCO approximation to get the wave function like this, and the cross section is can be used this formula. Therefore, we can get the cross section for molecular is related to this factor, and the cross section for atomic cross section. So we can get the interference factor, like use this formula. So we can observe the interference effect by plotting the interfactor. This figure shows the interfactor, so we can directly observe the interference factor in experiment. But for H2 molecular is very difficult. There are two reasons. One is the momental region of typical EMS spectrometer is relative low, maybe from 0 to 3.5 atomic unit. The other is the cross section is dropped down very rapidly in the large momentum. So it is very difficult for experiment to observe the interference effect. So we have two ways to attempt to observe the interference effect. One is we can choose a target with a large internuclear distance. This figure shows the different nucleations for this interfactor for different nuclear distance. So we can see when the distance is large, the interfactor is moved to the low momentum. So we can use the typical EMS spectrometer to observe the interference effect in the low moment region. This picture is shown just shown by last speaker. So it can be observed the interference effect from this picture. So the other way is we can compare interference factor at different nuclear distance. Maybe this means we can observe the movement of the interference region, like this picture shows. So the question is how to change the internuclear distance. One possibility is to do the vibrational revolution experiment. This is our motivation. So we did the vibrational resolved experiment on H2. This picture shows the experiment setup is used to do the vibrational EMS. Here is list the conditions and the performance of the setup. This picture shows the ionization process involved vibrational excitation from the ground stage to the final stage. This figure shows the binding energy spectra measured by photoelectron experiment. It can be shown that the vibration states of final states can be observed. This picture is showing the binding energy spectra measured by EMS. Although the revolution of the EMS spectrometer is not good enough to resolve the vibrational states, the Frank counting profiles shows the remarkable asymmetry. So we can try to get the experiment moment profiles for different states. Here is the experiment electron moment profiles for different vibrational states. On the other hand, we also calculation the vibrational resolved theoretical momentum profiles. This picture shows the experimental and theoretical momentum profiles for different vibrational states. From this picture, we can see that the agreement in shapes between experiment and theoretical results are reasonably good. Secondly, we can see that the general trait that the momentum profiles becomes fat with the increasing vibrational quantum numbers. So To highlight this difference, we plot the vibrational ratios of cross-section here. From this figure, we can get the ratios are distinguished for different vibration stages. But how to understand this difference? Let's come back to the theoretical calculations. Here is listed the formula is the transition matrix. For this factor, we can simplify it, use a simple approximation, which here the R is promised by the equilibrium internuclear distance. So we can get this ratio for different states should be consistent. But this figure for ratios for different students shows obvious deviations from Frank-Condon approximation. So how to explain this? These deviations from Frank values are also observed in the photoionization experiment. They ascribed this deviation to the Young type's interference. So, in order to explain this difference, we turn to the strange calculation for the vibrational resolved cross-section. Use this formula. Therefore, we can got the vibrational ratios of cross-section use this formula. This formula clearly shows that the ratio of the vibrational resolved cross-sections should be oscillation around the quotient of the Frank-Condon factor. So we can use this function to fit in the ratio. So we can say that the agreement of the model fitting with the measured and theoretical calculated vibrational ratios signifies the Young type state interference effect. In fact, to some extent, this also shows the movement of the interference fringes. Let's move to the part 3. In this part, we choose the target from simple diatomic molecular to the polyatomic molecules for looking multi-center interference. So so we can from the picture in order to observe the interference patterns with more periods, this need to extend the moment region. On the other hand, it also needs to improve the sensitivity of the EMS spectrometer because the cross-section is very low in the large moment ranges. So the high sensitivity EMS spectrometer with almost 2 pi angles detection is developed in our group. So the performance of the EMS spectrometer is measured through the measuring the ionization of argon. This figure is showing the argon orbital images, and this is the binding energy. We can, from this picture, two-dimensional energy and angular electron density map. We can got the electron momentum profiles. We can see that compared with the single channel measurement, this spectrometer, we can extend the momentum range up to 8 atomic units. Furthermore, the sensitivity of the spectrometer is improved up to 10 plus 10 odd 5. So, use this spectrometer, we can do some experiments on the polyatomic molecule to observe the interference effect. This picture shows the experiment results on CH4 molecules. This is the binding energy spectrometer. From these 2D maps, we can get the experimental electron momentum profiles for different molecular orbitals. Here is for HOMO and is for 42, and these 3 outermost molecular orbitals is composed of fluorine atomic orbitals. This molecular orbitals is non-bonding orbitals. So, in order to observe the interference, we can visualize the interference factor. This picture shows the interference factor. One can see the interference patterns are observed clearly with more periods. Furthermore, we can use this interference factor to fit in the experimental data and can be determined the distance between 2 fluorine atoms. For more details, please see our post MO 143 on July 27. This is the result of the NF3 molecular. So here it shows the energy and angular density maps. It's the binary spectrum. So we can also obtain the experimental electron moment profiles for different valence molecular orbitals, as shown here. Similarly, we can get the interference for these orbitals. One can see that from the figure, we can see the interference pattern is also observed clearly. And the distance of R is also determined to be about 3-point atomic unit by interference factor fitting. So we can get the geometry of the NF3. This picture shows the results of the SF6. This is the bi-energy spectra. So we can assignment the peak, use the peak, and to obtain the experiment electron momentum profiles, and then we also can obtain the interference factor. This figure also shows the interference factor. One can see the interference patterns are also observed clearly. So we can use the EMS experiment to observe the two-center Young-type interference effect, and also to observe the multi-center interference effect. So finally, I will give the summary. For H2 molecules, we did the vibrational resolved experiment, and the measured and calculated the vibrational ratios have revealed the deviations from Planck counting values, which can be ascribed to the oscillation in the vibrational ratios due to the Young-type interference effect. Also, we can look the movement of the interference fringe. It was shown that the vibrational resolved experiment provides a more straightforward way to observe Young-type interference in the electron impact ionization. So, for the polyatomic molecules, we can observe the multi-center interference patterns, and the distance between two fluorine atoms can be also determined by fitting the experimental data using the interference factor, which are generally in line with the values from the electron diffraction experiments. It also showing that AMS can also offer the feasible way to obtain the structural parameters of molecular by measuring the period of the interference fringe. So in the future, we move to our interest on the bonding orbitals of molecules to observe the interference effects. So thank you for your attention.